Right now, as you're watching this, something invisible is racing toward Earth at speeds that are extraordinary. You can't see it, you can't feel it, but it's here. Millions upon millions of charged particles racing across the void of space and colliding with our planet's magnetic shield at velocities that have doubled overnight. And the source? A massive dark opening has appeared on the surface of the Sun, a kind of cosmic opening that's pouring out a relentless stream of solar wind directly into Earth's path. This isn't science fiction. This is a real, ongoing event. This is happening right now, this very moment, and it's been building for hours while most of us went about our daily lives completely unaware. What makes this even stranger is that people across multiple states have already started reporting something they don't usually see. Brilliant curtains of green and red light dancing across the night sky. Aurora displays appearing far south of where they're normally visible. Something has changed in the space between us and the Sun, and scientists monitoring the data in real time are watching as our planet responds to forces that most of us never think about. The invisible architecture that protects us is being compressed, disturbed, reshaped by this high-speed stream, and while we're safe, the effects are rippling through systems both natural and technological. Stay with me, because in the next few minutes we're going to uncover exactly what's happening above our heads, why a giant hole on the Sun is sending a particle stream directly at us, what it means for the auroras lighting up the sky, and why this isn't just a rare cosmic accident. It's part of a pattern that's becoming more common as our Sun moves through a particularly active phase of its life. But first, let me give you the immediate picture. There's a stream of solar wind. Not wind like you'd feel on your face, but a river of electrified particles that left the Sun days ago and reached Earth with timing that seems almost intentional. It arrived with force, carrying energy and momentum that our magnetosphere, that invisible bubble of magnetic fields surrounding our planet, has to absorb and redirect. The speed of this stream is roughly double what we'd consider normal background solar wind, and that difference matters enormously. It's the difference between a gentle breeze and a gale, between calm seas and storm surge, and the reason for this surge traces back to something that opened up on the Sun itself. A feature so large and so dark in the images captured by solar observatories that it looks like the Sun has an opening, like something created a hole in its surface. Of course, it's not a hole in the way you might imagine. The Sun hasn't been punctured, but what's happened is in some ways even more fascinating because it reveals the dynamic, violent, constantly shifting nature of the star that gives us life. This dark region, this coronal hole as scientists call it, is a place where the Sun's magnetic field has opened outward instead of looping back on itself, and through that opening, particles that would normally be trapped close to the solar surface are escaping into space at extraordinary speeds. And because of the rotation of the Sun and the position of Earth in its orbit, we've moved directly into the path of that escaping stream. The timing is remarkable. The stream intensified throughout the day yesterday, built momentum through the evening, and peaked overnight between the 8th and 9th of January 2026. While many of us were sleeping, the solar wind speed climbed and climbed, reaching levels that trigger what's called a geomagnetic storm, a disturbance in Earth's magnetic field, strong enough to create auroras, strong enough to affect satellite operations, strong enough that power grid operators and communication systems have to pay attention. And here's what makes this moment particularly compelling. This isn't over. The stream is still hitting us. Earth is still positioned in the outflow from that coronal hole, and forecasters expect the effects to continue through at least today and into tomorrow. You might be wondering why you haven't heard emergency sirens, why there's no panic in the streets, and that's because Earth has been dealing with solar wind since long before humans walked upright. Our planet's magnetic field is ancient, shaped over billions of years, and it's remarkably good at its job. It takes the incoming stream of charged particles and deflects most of them around the planet, like water flowing around a stone in a river. But that deflection creates pressure, creates disturbances, and those disturbances manifest as geomagnetic storms and as auroras, those stunning light displays that have captivated humanity for millennia. What's different now, what makes this moment worth paying attention to, is that we live in a technological civilization. We have satellites orbiting in the very regions where these particle streams are most intense. We have power grids that can be affected by the currents induced in Earth's magnetic field during strong storms. We have GPS systems that rely on precise measurements of signals passing through the ionosphere, and the ionosphere gets disturbed when geomagnetic storms occur. So while our ancestors might have simply marveled at the auroras and woven them into mythology, We have to monitor, predict, and sometimes protect our infrastructure from these invisible forces. And beyond the practical considerations, there's something deeply compelling about this moment. We're living through an event that connects us directly to the sun, that reminds us we're not isolated on this little blue marble, but are constantly bathed in radiation and particles from a star 93 million miles away. That star is dynamic, violent, beautiful in its fury, and it's going through a phase right now where these kinds of events are becoming more frequent. The sun operates on a cycle, roughly 11 years from one peak of activity to the next, and we're currently near the peak of solar cycle 25. That means more sunspots, more eruptions, more coronal holes, more opportunities for Earth to find itself in the path of enhanced solar wind streams. So as you're watching this, particles that left the sun days ago are arriving at Earth, compressing our magnetic field, creating disturbances that ripple through the space around our planet, funneling down into the polar regions where they collide with atoms in our atmosphere and create light, those mesmerizing auroras that people are already photographing and sharing on social media. And all of this traces back to that dark opening on the sun, that coronal hole that appeared, rotated into position, and sent a high-speed stream directly toward us. I want you to understand what that means, not just in terms of data and measurements, but in terms of what it reveals about the universe we live in. Because this isn't a random accident. This is the way our solar system works. The sun breathes, in a sense. It expands and contracts, its magnetic field shifts and reorganizes, and periodically it opens pathways through which its material can escape into space. We happen to be close enough, positioned just right, to feel those effects. We're going to dive deep into the numbers, the mechanisms, the science behind what's happening. We're going to explore why that hole formed, what makes the solar wind speed up, what happens when it collides with Earth, and what we can expect in the days ahead. But before we move forward, I want to ask something of you. If this kind of content fascinates you, if you want to stay informed about what's happening in the space around us, hit that subscribe button right now. This is a story that's unfolding in real time, and there will be more to cover as the solar wind continues to impact Earth, as other events develop, as the sun remains in this active phase. And drop a comment telling me where you're watching from, whether you're in one of the northern states where auroras have been visible, or whether you're further south, watching with curiosity as these invisible forces play out above your head. We're all experiencing this together, all living under the same star, all connected by the fact that right now, our planet is being buffeted by a stream of particles from a giant dark hole on the sun. Let's explore this together. What I'm about to show you in the next several minutes will change the way you think about the sun, about space weather, about the invisible forces that shape our world. You'll understand why this moment matters, why scientists are watching closely, and why this isn't the last time we'll see something like this. Because the truth is, this is becoming the new normal as we move deeper into solar maximum, and understanding what's happening now will prepare you for what's coming next. Let's talk about speed, but not the kind you experience driving down a highway or watching a plane take off. We're talking about particles moving through the vacuum of space at velocities that are almost incomprehensible to our everyday experience. The solar wind, under normal circumstances, flows constantly from the sun toward Earth and beyond, at speeds around 400 kilometers per second. That's already fast, over 1 million kilometers per hour if you want to put it in those terms. It's fast enough that material leaving the sun reaches Earth in just a few days, crossing that vast distance of space as if it were nothing. But right now, the solar wind isn't moving at normal speed. Right now, it's moving at roughly double that rate, and that difference is everything. When scientists monitoring space weather data saw the numbers climbing yesterday, they knew immediately that something had changed. The instruments stationed between Earth and the Sun, satellites positioned at a gravitationally stable point where they can constantly measure the incoming solar wind, started registering velocity increases that couldn't be ignored. The stream that had been flowing at a steady background rate began to accelerate, and that acceleration meant one thing. Earth was moving into the outflow from a high-speed stream source on the Sun. The particles themselves are charged, mostly electrons and protons, the fundamental components of atoms stripped down to their bare essentials by the Sun's intense heat. They're electrically charged, which means they interact with magnetic fields, and that interaction is what creates all the downstream effects we're seeing. But let's not get lost in the physics just yet. The key point here is contrast. Imagine you're standing by a river, watching the water flow past at a relaxed pace. You could wade in, the current would move around you, but it wouldn't knock you over. That's the normal solar wind. Now imagine that same river suddenly surging, the water level rising, the speed doubling, the force increasing exponentially. You wouldn't want to wade in anymore. You'd feel the power, the potential for disruption. That's what's happening in space right now. Earth's magnetosphere is that person standing by the river, and the river just became a torrent. The numbers themselves tell a story. The velocity measurements climbed steadily through the day on January 8th, moving from baseline levels into the range that triggers geomagnetic storm watches. By overnight, the speed had peaked, hitting levels that fall into the category of a significant high-speed stream event. And here's what makes this more than just an academic exercise in measurement. Those speeds translate directly into energy. When fast-moving particles slam into Earth's magnetic field, they transfer momentum, they create pressure, they disturb the delicate balance that normally exists in the space around our planet. And those disturbances propagate, rippling through the magnetosphere, funneling energy down into the polar regions, exciting atoms in the upper atmosphere and creating light. So what exactly is solar wind? If it's not wind in the way we usually understand it, think of it as a stream of charged particles constantly flowing outward from the sun in all directions. The sun is so hot, so energetic, that atoms in its outer atmosphere, the corona, are moving fast enough to escape the sun's gravity entirely. They don't orbit, they don't fall back, they just keep going, streaming outward into the solar system, and because the sun is a ball of plasma, of electrically charged gas, it carries a magnetic field with it, and that magnetic field gets dragged along with the outflowing particles. This creates what's called the interplanetary magnetic field, a structure that fills the space between planets and influences everything from cosmic rays to auroras. Under normal conditions, this outflow is relatively steady. The sun breathes it out constantly, and Earth sits in that breeze protected by its own magnetic field. But the sun isn't uniform. Its surface is dynamic, covered in regions of intense magnetic activity, and some areas have magnetic configurations that allow particles to escape much more easily than others. These are the coronal holes, and when Earth's orbit carries us into alignment with one, we don't just get the normal solar wind. We get a high-speed stream, a concentrated flow of particles moving significantly faster than the background. And that's exactly what's happening right now. The satellites that measure this, like the ones positioned at the first Lagrange point between Earth and the Sun, are constantly streaming data back to researchers. They measure not just the speed, but the density of particles, the strength of the magnetic field embedded in the solar wind, the temperature, the composition. All of that data gets analysed in real time, and forecasters use it to predict what will happen when those conditions reach Earth, because the satellites give us about an hour's warning before the solar wind actually impacts our magnetosphere. It's like having a weather station upstream on a river, letting you know when a surge is coming so you can prepare downstream. And the data from the past day has been unambiguous. The speed increased, the density remained relatively high, and the magnetic field carried by the solar wind had a configuration that allowed it to couple efficiently with Earth's magnetosphere. That coupling is critical, because not all solar wind creates strong geomagnetic effects. If the magnetic field in the solar wind is oriented in a certain way, it can connect with Earth's magnetic field and peel back the outer layers of the magnetosphere, allowing energy and particles to penetrate deeper. If it's oriented differently, the solar wind can flow past with relatively little disturbance. But the stream we're dealing with now has been oriented favourably for creating disturbances, which is why the effects have been so pronounced. The peak occurred overnight, which means many people were asleep when the solar wind speed reached its highest values. But the instruments never sleep, and the Aurora watchers who stay up late or wake up early were rewarded with displays that aren't normally visible at their latitudes. The geomagnetic storm conditions that result from these high-speed streams are classified using various indices, and the levels reached overnight were enough to push us into moderate storm territory. Not the strongest possible, not the kind of storm that causes widespread infrastructure problems, but significant enough that auroras expanded southward, satellite operators took notice, and anyone monitoring space weather knew something substantial was happening. What's important to understand is that this isn't instantaneous. The solar wind doesn't hit Earth like flipping a light switch. The stream arrived, the magnetosphere began to respond, and over the course of hours the disturbances built. The particles that make it past the magnetosphere's outer defenses get funneled along magnetic field lines toward the poles, where the field lines converge and dive down into the atmosphere. That's where the auroras form, in a ring around the magnetic poles, and the stronger the geomagnetic storm, the farther from the poles that ring expands. So people in states that rarely see auroras suddenly found themselves looking up at shimmering curtains of light, posting photos, wondering what was happening. What was happening was the solar wind, moving at double its normal speed, delivering energy into Earth's space environment faster than the magnetosphere could quietly absorb it. And the stream hasn't stopped. As of right now, the solar wind speed remains elevated. It's not at the overnight peak anymore, but it's still significantly above normal, and forecasters expect it to remain that way through at least the next day or two. Why? Because Earth is still positioned in the outflow from that coronal hole on the Sun. The hole opened, it's large, and it's rotating with the Sun's surface. As long as Earth remains in the path of the fast stream emanating from that hole, we'll continue to experience these effects. The solar wind will continue to batter our magnetosphere, the geomagnetic conditions will remain disturbed, and the auroras will continue to appear for those at the right latitudes. But numbers alone don't capture the full picture. Yes, the speed doubled. Yes, the measurements confirm a high-speed stream event. But what does that actually mean for us, for the space around our planet, for the systems we rely on? That's where the story gets more interesting, because the solar wind doesn't just pass by harmlessly. It interacts, it disturbs, it reshapes the magnetic environment around Earth in ways that cascade into observable effects. And understanding those effects requires us to zoom in on the source, to look at what happened on the Sun itself to create this stream. Because the numbers don't lie. Something opened up on the Sun, something vast and dark, and it's pouring particles into space like a cosmic fire hose aimed directly at us. So now that you understand the speeds involved, now that you know this isn't normal background solar wind but something significantly more powerful, let's turn our attention to the Sun itself. Let's look at what appeared on its surface, what created this high-speed stream, and why a giant dark region has become the focus of every space weather forecaster watching our star. Because the solar wind is just the symptom. The cause is something far more fascinating, something that reveals the true nature of the Sun as a dynamic, magnetic, constantly evolving entity. And that cause is a coronal hole, a feature that looks like a wound but is actually a window into the processes that govern our star's behaviour. When solar astronomers look at the Sun through specialised instruments, they're not seeing the bright white disk that we glimpse during the day. They're observing in wavelengths of light invisible to the human eye, ultraviolet and X-ray emissions that reveal the Sun's outer atmosphere, the corona, in stunning detail. And in those images, taken by spacecraft like the Solar Dynamics Observatory, that continuously monitor our star, a massive dark region has appeared. It stretches across the Sun's equator, a vast area where the normally bright corona looks dim, almost black by comparison. To someone unfamiliar with solar physics, it might look like the Sun has been damaged, like something punched a hole clean through its surface. But that's not what's happening. What we're seeing is a coronal hole, and it's not an absence of material, it's a window into a completely different magnetic configuration. Let me explain. The Sun's corona, that outer atmosphere extending millions of kilometers into space, is incredibly hot. Far hotter than the Sun's visible surface. It's heated to temperatures where atoms are stripped of their electrons, where matter exists as plasma, and where magnetic fields dominate the behavior of everything. Under normal circumstances, the magnetic field near the Sun's surface forms closed loops. Magnetic field lines emerge from one region, arc through the corona, and dive back down into another region, creating structures that trap plasma close to the Sun. These closed loops are bright in ultraviolet images because they're filled with hot, dense plasma that radiates intensely. But in a coronal hole, the magnetic field configuration is fundamentally different. Instead of looping back, the field lines open outward, stretching into space without returning to the Sun's surface, and where the field is open, plasma can escape freely. That's why coronal holes appear dark. It's not that there's no material there, it's that the material isn't trapped. It's flowing outward, streaming into space along those open magnetic field lines, and because it's not confined, the density drops, the temperature decreases slightly, and the emission of ultraviolet light falls dramatically. So when we see that dark region on the Sun, What we're really seeing is an area where the sun is actively bleeding plasma into the solar system at high speeds. It's like a valve opened, releasing pressure, and everything downstream of that valve gets hit by the outflow. The coronal hole currently facing Earth is particularly significant because of its size and position. It's what scientists call a transequatorial coronal hole, meaning it stretches across the sun's equator rather than being confined to the polar regions. The sun's poles almost always have coronal holes. Those are relatively stable features. But when a coronal hole forms near the equator and expands across it, that's when Earth is most likely to move into its stream, because Earth's orbit lies roughly in the plane of the sun's equator. And this hole has rotated into the perfect position. As the sun spins on its axis, completing a rotation roughly every month, features on its surface rotate into and out of view from Earth's perspective. And days ago, this coronal hole rotated into a position where its outflow is aimed directly at us. Imagine standing next to a rotating sprinkler, the kind that spins and sprays water in all directions. Most of the time, the spray misses you, but as it rotates, there's a moment when the jet of water points right at you, and suddenly you're drenched. That's essentially what's happening with the coronal hole. The sun rotates, the hole rotates with it, and Earth has moved into the path of the high-speed stream emanating from that open magnetic region. And because the hole is large, the stream is broad and long-lasting. We're not just getting a brief hit, we're sitting in the stream for days as the geometry slowly changes and the hole rotates past. The magnetic nature of coronal holes is crucial to understanding why the solar wind from these regions moves so fast. In areas where the magnetic field is closed, plasma is trapped, constrained, held close to the sun by magnetic forces. It can't easily escape, so it builds up density and pressure. But in a coronal hole, the open magnetic field provides a highway for plasma to leave, and not just leave slowly, accelerate. The particles near the base of the corona are already moving at high thermal velocities because of the extreme temperatures, and when those field lines open, there's nothing to stop them from flowing outward. They accelerate as they move away from the sun, reaching speeds far higher than the solar wind from closed field regions. By the time that stream crosses the distance to Earth, it's moving at roughly double the normal solar wind speed, which is exactly what we're measuring now. This isn't a rare phenomenon in an absolute sense. Coronal holes form regularly, especially during the active phases of the solar cycle, but their impact on Earth depends entirely on their position and timing. A large coronal hole near the sun's poles won't affect us much because its stream shoots above or below the plane of Earth's orbit. But one near the equator, one that rotates into alignment with Earth, that's when we feel the effects. And the current solar cycle has been producing more of these equatorial coronal holes as the sun's magnetic field becomes more complex and tangled during solar maximum. What you're seeing in those ultraviolet images of the sun right now is the result of magnetic processes happening beneath the surface. The sun doesn't have a solid surface like Earth. It's gas and plasma all the way down to the core. But the layers where energy is transported by convection, the outer layers where plasma churns and circulates, those layers generate magnetic fields through a dynamo process. Charged plasma moving in circulating patterns creates electric currents, and electric currents generate magnetic fields. The sun's rotation twists those fields, tangles them, and periodically they emerge through the visible surface, creating sunspots and active regions. And in some places, the field configuration allows for those open structures, coronal holes, where the field lines stretch into interplanetary space. The hole we're dealing with now formed as the sun's magnetic field reorganized. During solar maximum, the sun's field is chaotic, constantly shifting. Magnetic flux emerges and cancels, loops form and collapse, and occasionally the field settles into a configuration that supports a large open region. Once formed, a coronal hole can persist for weeks or even months, though they evolve over time. They can grow, shrink, merge with other holes, or disappear as the underlying magnetic field changes. But while they're present, they're prolific generators of high-speed solar wind, and they rotate with the sun, sweeping their streams across the solar system, like a lighthouse beam sweeping across the ocean. And here's something remarkable. If you were to track the rotation of the sun and the position of this coronal hole, you'd realize that Earth's encounter with its stream was predictable. Solar physicists saw the hole forming, watched it rotate toward Earth-facing position, and issued forecasts days in advance that a high-speed stream would arrive around January 8th or 9th. They couldn't predict the exact intensity or how well the magnetic field would couple with Earth's magnetosphere, but they knew the stream was coming, and sure enough, it arrived right on schedule, a testament to our growing understanding of how the sun works and how its activity propagates through space. But understanding that a coronal hole is the source raises another question, one that's even more fundamental. Why do these holes form in the first place? What causes the sun's magnetic field to organize itself into these open configurations? Why does the sun, in a sense, tear itself open and allow its material to stream into space? That question takes us deeper into the life cycle of the sun, into the magnetic forces that govern stellar behavior, and into the current phase of the solar cycle that's making events like this more common. Because the formation of coronal holes isn't random. It's a direct consequence of the sun operating at a high level of magnetic activity, and that's exactly where we are right now as solar cycle 25 continues to build toward its peak. The dark region you're seeing on the sun in those images isn't a scar or a wound. It's a manifestation of the sun's magnetic heartbeat, the visible sign of processes that have been occurring inside the sun for millennia, processes that affect every planet in the solar system. And now, with Earth positioned directly in the path of the stream from that hole, we're feeling those effects firsthand. The solar wind speed doubled, the magnetosphere responded, the auroras appeared, and all of it traces back to that dark opening on the sun's surface, where the magnetic field opened outward and released a torrent of particles into space. And to truly understand why this matters, why this isn't just an interesting curiosity but a window into the dynamic nature of our star, we need to explore the magnetic forces at play, the solar cycle we're currently experiencing, and why the sun is behaving the way it is right now. The sun is not a static object. It's not a steady, unchanging ball of fire sitting passively in space. It's a roiling, dynamic, magnetically complex star that operates on cycles and rhythms that govern its behavior over years and decades. And right now, the sun is in a phase where its magnetic field is tangled, chaotic, and constantly reorganizing. That chaos is what leads to coronal holes, sunspots, solar flares, and all the phenomena we group under the term space weather. To understand why that dark hole opened on the sun, why the magnetic field configured itself to allow high-speed solar wind to escape, you have to understand the solar cycle and the magnetic forces that drive it. The sun operates on an 11-year cycle, roughly speaking, though the length and intensity vary from one cycle to the next. At the start of a cycle, the sun is quiet. There are few sunspots, few eruptions, few coronal holes near the equator. The magnetic field is relatively organized, with clear north and south magnetic poles, much like Earth has. But as the cycle progresses, the sun's internal dynamo, the process by which motion in the sun's interior generates magnetic fields, starts to amplify the field strength. Magnetic flux rises to the surface, creating sunspots and active regions. The field becomes more tangled as the sun's differential rotation, the fact that the equator rotates faster than the poles, winds up the magnetic field lines like twisting a rubber band. As the cycle reaches its peak, solar maximum, the magnetic field becomes incredibly complex. The number of sunspots increases, active regions proliferate, and the sun's magnetic poles actually flip. North becomes south, south becomes north, a complete reversal that marks the height of the cycle. And in this chaotic magnetic environment, coronal holes form with greater frequency, especially near the equator where their streams are most likely to impact Earth. The magnetic field lines that were once closed, looping back to the surface, can snap and reconnect in configurations that allow them to open outward. When that happens, a coronal hole forms. Think of it like releasing tension. The sun's magnetic field is under enormous stress during solar maximum, twisted and tangled by the constant motion of plasma beneath the surface. Occasionally, that field reorganizes in a way that releases some of that stress, allowing field lines to open and material to escape. It's the sun's way of exhaling, of shedding excess energy and plasma into space. And for the planets in the path of that exhalation, the effects are immediate and noticeable. We're currently in solar cycle 25, a cycle that officially began in late 2019. For the first few years, activity was relatively low, as expected. But starting in late 2023 and continuing into 2024, and now into early 2026, the sun has been ramping up its activity significantly. The number of sunspots has increased, solar flares and coronal mass ejections have become more common, and coronal holes have been forming near the equator with increasing regularity. Forecasters initially predicted that solar cycle 25 would be a relatively weak cycle, but the Sun has defied those predictions. Activity levels have been higher than expected, and some indicators suggest we're already at or near solar maximum, even though the cycle isn't halfway through its expected lifespan yet. The magnetic poles of the Sun have already flipped during this cycle, which is a key marker of solar maximum. That flip doesn't happen suddenly. It's a gradual process where the field weakens, becomes disorganized, and then reorganizes with the opposite polarity. And when the field is in that chaotic state, that's when we see the most activity. The coronal hole currently facing Earth is a product of that chaotic field. The underlying magnetic structure shifted, field lines opened, and a vast region of the Sun's corona became a source of high-speed solar wind. But here's what's important to understand. This is normal solar behavior. It's not a catastrophe, not a sign that something is wrong with the Sun. Stars like the Sun experience these cycles as a natural consequence of being magnetized balls of plasma. The dynamo process that generates the magnetic field also causes it to vary in strength and complexity over time. The Sun has been doing this for billions of years, long before Earth had life on its surface, and it will continue doing it for billions more. What's different now is that we're here to observe it, to measure it, and to feel its effects on our technological civilization. The magnetic forces at play are immense. The Sun's magnetic field, when it emerges through the surface in the form of a sunspot, can be thousands of times stronger than Earth's magnetic field. Those fields can store enormous amounts of energy, and when they reorganize, when field lines reconnect in new configurations, that energy gets released suddenly, sometimes explosively. That's what causes solar flares and coronal mass ejections. But in the case of coronal holes, the reorganization is more gradual, more stable. The field lines open, and instead of a sudden explosion, you get a steady stream, a high-speed wind that flows for days or weeks, as long as the coronal hole persists. And the fact that we're in solar maximum means we can expect more of this. More coronal holes will form, rotate into Earth-facing positions, and send their streams our way. More high-speed solar wind events will occur, more geomagnetic storms will develop, and more auroras will light up the skies at latitudes that don't usually see them. This isn't a one-time event. It's part of a pattern that will continue for the next year or two, as the Sun remains in its active phase. Eventually, as the cycle progresses past maximum and into the declining phase, activity will decrease. The magnetic field will become more organized again, coronal holes will retreat toward the poles, and the frequency of Earth impacts will drop. But that's still years away. For now, we're living through the peak, and the Sun is reminding us that it's not just a passive provider of light and heat. It's an active, dynamic star that shapes the space environment around all the planets. The opening of coronal holes is also influenced by the evolution of active regions on the Sun. Sometimes a coronal hole will form adjacent to or in the wake of a decaying active region, as if the magnetic field is reorganizing after the intense activity subsides. Other times, holes form in areas that seem quiet, with no obvious precursor. But in all cases, the underlying cause is the same. The magnetic field configuration changes in a way that allows field lines to open, and once they're open, the solar wind accelerates along them, creating the high-speed streams we're detecting now. What's fascinating is that despite all our advances in solar physics, despite the spacecraft observing the Sun in unprecedented detail, there's still much we don't fully understand about coronal holes. We know they form, we know they produce high-speed wind, but the exact mechanisms that heat the solar wind to such high speeds as it escapes are still debated. We know the corona is incredibly hot, but we don't fully understand why. We know magnetic fields are central to the process, but the details of how energy gets transferred from the Sun's interior to the corona and then into the solar wind involve complex physics that's still being unraveled. Every observation, every high-speed stream event like the one we're experiencing now, adds data to the puzzle, bringing us closer to a complete understanding of how our star works. And that brings us back to the present moment. The Sun has opened a massive coronal hole, the magnetic field configuration allows high-speed solar wind to escape, and Earth has moved into the path of that stream. The particles are arriving now, have been arriving for hours, and will continue arriving for at least another day or two. And when those particles reach Earth, when that stream of charged plasma slams into our magnetosphere, a whole cascade of effects begins. The magnetosphere compresses, disturbances propagate through it, energy funnels toward the poles, and the atmosphere lights up with auroras. The solar wind doesn't just pass by, it interacts, it affects, it reshapes the space around our planet. And understanding what happens during that interaction is key to understanding why space weather matters, why we monitor it so closely, and why events like this are more than just pretty lights in the sky. Earth is not alone in space. It's surrounded by a protective bubble, an invisible shield generated by our planet's molten iron core. As that core churns and circulates, it generates a magnetic field that extends tens of thousands of kilometers into space, forming what's called the magnetosphere. This field is our first line of defense against the solar wind, and under normal conditions, it does its job quietly. The solar wind flows around it like water around a stone, deflected outward, prevented from directly impacting our atmosphere. But when a high-speed stream arrives, when the solar wind speed doubles and the pressure on the magnetosphere increases dramatically, everything changes. The magnetosphere is dynamic, not rigid. It can compress, stretch, and deform depending on the conditions in the solar wind. And when that fast stream hit Earth over the past day, the first thing that happened was compression. The increased pressure pushed inward on the sunward side of the magnetosphere, squeezing it, bringing the boundary closer to Earth. On the opposite side, the night side, the magnetosphere stretched out into a long tail, forming a structure that extends far into space downstream of Earth. This compression and stretching create disturbances, ripples of energy that propagate through the magnetosphere like waves moving through water. And those disturbances don't stay confined to the outer reaches. They travel inward, affecting regions closer to Earth, and eventually they funnel down toward the poles. Here's why the poles matter. Earth's magnetic field lines emerge from one pole, arc out into space, and converge back down into the other pole. They form closed loops, but the geometry means that the field lines get closer together, more concentrated near the polar regions. And when particles from the solar wind manage to penetrate the outer magnetosphere, either because the magnetic field in the solar wind is oriented in a way that allows reconnection, or because turbulence in the magnetosphere allows particles to leak inward, those particles get guided along the field lines toward the poles. They spiral along the magnetic field, accelerating as they descend, and eventually they collide with atoms and molecules in the upper atmosphere. That collision is what creates auroras. When a charged particle from the solar wind slams into an oxygen atom or a nitrogen molecule at high altitude, it transfers energy. The atom or molecule gets excited, kicked into a higher energy state, and when it relaxes back to its normal state, it releases that energy as light. Oxygen produces green and red emissions depending on altitude and energy. Nitrogen produces blue and purple hues. The result is those shimmering curtains of light that have captivated humans for millennia, the Aurora borealis in the northern hemisphere and Aurora australis in the southern hemisphere. And during geomagnetic storms, when the solar wind is particularly strong and the disturbances in the magnetosphere are intense, those auroral ovals expand away from the poles, allowing people at lower latitudes to witness the display. That's exactly what happened over the past night. As the high-speed stream impacted Earth, as the magnetosphere compressed and disturbances built, the auroral ovals expanded southward. People in northern states across the US reported seeing auroras, some for the first time in their lives. Social media lit up with photos of green glows on the horizon, shimmering arcs overhead, vibrant displays that wouldn't normally be visible so far from the Arctic. And those reports weren't coming from Montana or North Dakota alone. They extended into states where auroras are rare. Proof that the geomagnetic storm was significant enough to push the auroral oval far beyond its typical boundaries. The intensity of a geomagnetic storm is measured using several indices, but one of the most commonly referenced is the Kindex, a scale that runs from 0 to 9. Low values, 0 through 3, indicate quiet conditions. Values of 4 or 5 indicate minor to moderate storms. 6 and above indicate strong to extreme storms. The current event pushed the Kindex into the moderate storm range, high enough to create widespread auroras but not high enough to cause major infrastructure concerns. At higher levels, geomagnetic storms can induce currents in power lines, potentially leading to transformer damage. They can disrupt satellite operations, increase drag on low Earth orbit spacecraft, and interfere with radio communications, especially high-frequency systems used in aviation and maritime operations. But at the levels we've experienced, the effects are more subtle. Increased auroras, minor satellite anomalies, slight GPS inaccuracies. Still, the fact that those effects are present at all is a reminder that we live in a space environment that's constantly influenced by the sun. Our technology operates in that environment, and during geomagnetic storms, operators of satellites, power grids, and communication systems have to pay attention. Satellite operators might adjust orbits or switch to backup systems. Power grid managers might monitor transformer currents more closely. GPS systems might see slight decreases in accuracy because the ionosphere, the layer of Earth's atmosphere where GPS signals travel, becomes disturbed during storms. The charged particles that create auroras also affect the ionosphere's density and structure, and that can delay or distort signals passing through it. But beyond the technical concerns, there's something profoundly beautiful about what's happening. Earth is being bathed in a stream of particles from the sun, and instead of simply absorbing that energy invisibly, our planet responds with light. The interaction between solar wind and magnetosphere creates one of nature's most stunning visual phenomena. Auroras are a reminder that Earth is not isolated, not separate from the rest of the solar system. We're connected to the sun by invisible threads of magnetic field and flowing plasma, and occasionally those connections become visible, manifest as glowing ribbons of colour dancing across the polar skies. The auroras that people are seeing now are a direct result of the solar wind speed doubling, of the coronal hole on the sun opening and sending a high-speed stream directly toward us. Without that stream, the magnetosphere would be quiet, the auroral ovals would remain small and confined to high latitudes, and most people would never witness the phenomenon. But with the stream impacting Earth, with the magnetosphere compressed and disturbed, the auroras have expanded, intensified, and become visible to millions of people who might not otherwise have the chance to see them. And that opportunity will continue for at least another night or two, as long as Earth remains in the path of the coronal hole's outflow. The geometry of the situation matters. As the sun rotates, the coronal hole rotates with it, and the stream it produces sweeps across space like a rotating jet of water. Earth entered that stream, and for a window of time we're sitting in the fast flow. Eventually, as the sun continues to rotate, the stream will sweep past us. The solar wind speed will drop back to normal levels, and the geomagnetic disturbances will subside. The auroras will retreat northward, the kindex will fall, and the magnetosphere will relax back into its typical configuration. But that hasn't happened yet. Right now, the stream is still hitting us, the effects are still ongoing, and anyone at the right latitude with clear skies has a chance to look up and see the interaction between Earth and Sun playing out in real time. And it's worth emphasizing, this is a natural process. Earth has been experiencing geomagnetic storms for as long as it's had a magnetic field, which is billions of years. Life evolved under these conditions. The auroras have been lighting up the skies since before humans existed. What's different now is our awareness, our ability to measure and predict, and our dependence on technology that's vulnerable to these disturbances. But the process itself is ancient, fundamental, and in its own way, beautiful. The sun sends out its wind, Earth's magnetic field deflects it, and in the process, energy gets transferred, light gets emitted, and we're reminded that we live on a planet embedded in a dynamic, constantly changing space environment. As the stream continues to flow, as the magnetosphere continues to respond, the story isn't over. The peak may have passed overnight, but the effects are lingering, and forecasters are watching to see how conditions evolve over the next day. Will the stream intensity hold steady, or will it gradually decline? Will another burst of faster wind arrive if the coronal hole structure changes? These are questions that space weather forecasters are asking right now, monitoring the data from satellites, running models of the magnetosphere, and issuing updates to anyone who needs to know. And beyond the immediate effects, there's a broader context to consider. This event is part of a pattern, part of the larger story of solar maximum and what it means for Earth in the months and years ahead. Because this high-speed stream is not an isolated incident. It's one of many that we can expect as the sun continues its active phase, and understanding what comes next requires us to look forward, to consider what the forecasts are telling us, and to recognize that we're living through a period of heightened solar activity that will shape space weather for some time to come. There's something compelling about events that unfold while most people are asleep, oblivious to the forces at play above their heads. While millions slept through the night of January 8th into the 9th, the solar wind speed reached its peak. The magnetosphere compressed to its maximum extent, and auroras blazed across northern skies. For those who stayed awake, who ventured out into the cold darkness armed with cameras and curiosity, it was a night to remember. Reports started filtering in through the early morning hours, sightings from across the northern states, photos posted online showing green curtains shimmering above the horizon, excited messages from people who had never seen an aurora before and couldn't quite believe what they were witnessing. The timeline of this event is a study in how space weather unfolds. It doesn't happen suddenly, like a lightning strike. It builds gradually as conditions align. Days ago, solar observers watched the coronal hole rotate toward Earth-facing position and issued forecasts that a high-speed stream would arrive around January 8th. The exact timing is always uncertain because predicting the precise structure of the solar wind as it propagates across space is challenging. But the general window was clear, and as January 8th progressed, the data from satellites between Earth and the Sun confirmed that the stream was arriving. Solar wind speed began to climb from its baseline levels, steadily increasing through the afternoon and evening. By late evening, the speed had reached levels that forecasters knew would produce geomagnetic storm conditions. The magnetosphere began to respond, compressing under the increased pressure, and the disturbances started to build. The kindex, that measure of geomagnetic activity, started to climb, and then, overnight, the stream reached its peak velocity. The instruments recorded values roughly double the normal solar wind speed, and the magnetic field embedded in the solar wind had an orientation that allowed efficient coupling with Earth's field. That combination, high speed and favourable magnetic orientation, is what produces the strongest geomagnetic storms, and it's what happened overnight. For aurora watchers, the timing was challenging. The peak occurred in the early morning hours, when fatigue sets in and the coldest temperatures settle over northern regions. But those who braved the conditions were rewarded. The auroral oval expanded southward, driven by the intense energy being funneled into the magnetosphere from the solar wind. States that rarely see auroras found themselves under shimmering displays. The colours were vivid, bright greens dominating with hints of red at higher altitudes where oxygen emissions shift wavelength. Cameras captured what the naked eye sometimes struggles to see, revealing structures and details in the aurora that appear faint to human vision but stand out brilliantly in long-exposure photographs. And the reports didn't just come from traditional aurora hotspots. They came from communities farther south, from places where most residents have never seen the northern lights, from latitudes where the phenomenon is so rare that it becomes a once-in-a-decade or once-in-a-lifetime event. That's the hallmark of a significant geomagnetic storm, the expansion of the auroral oval to regions where it's newsworthy, where it breaks the routine of daily life and becomes something people talk about, share, and remember. And social media amplified the experience, turning individual sightings into a collective event, a shared moment of wonder as people across multiple states looked up and saw the same thing happening in the sky. But the peak, as intense as it was, didn't last indefinitely. By the time dawn broke, the solar wind speed had begun to ease slightly, not back to normal, but down from the overnight maximum. The kindex started to decline, though it remained elevated, indicating that geomagnetic storm conditions were persisting even if the most intense phase had passed. And that's typical of high-speed stream events. They don't hit suddenly and disappear. They build, peak, and then gradually subside as Earth rotates and the stream's geometry changes. The coronal hole is still there, still sending out fast solar wind, but the most intense part of the stream passed by overnight, and what remains is a trailing edge, still faster than normal but not as extreme as the peak. As January 9th progressed, the situation remained active. The solar wind speed stayed elevated well above baseline, and the magnetosphere continued to experience disturbances. Auroras remained visible at high latitudes, though perhaps not as intense or as far south as they were during the overnight peak. Forecasters issued updates indicating that conditions would likely remain disturbed through at least another night, giving those who missed the overnight display another opportunity to see auroras if they were positioned in the right location. And indeed, as evening approached on the 9th, aurora watchers were out again, scanning the northern horizon for any signs of activity, hoping for a repeat of the previous night's show. But beyond the auroras, the timeline reveals something important about how space weather operates. There's a rhythm to it, a sequence of events that follows predictable patterns once you understand the underlying causes. The coronal hole formed, rotated into position, and sent out its stream. That stream propagated across space at high speed, taking days to cross the distance from Sun to Earth. When it arrived, it didn't impact Earth instantly. It took time for the magnetosphere to fully respond, for the disturbances to build, for the energy to funnel into the auroral zones. The peak occurred overnight, and then conditions began to gradually subside. And through it all, the instruments kept recording data, the forecasters kept issuing updates, and the community of space weather enthusiasts kept watching, learning, and sharing what they observed. What makes this timeline particularly interesting is that the solar wind event isn't happening in isolation. While the high-speed stream from the coronal hole was impacting Earth, other solar activity was also occurring. There were reports of a filament eruption on the Sun, a different type of event where a structure of cool plasma embedded in the corona becomes unstable and erupts outward. Filament eruptions can sometimes produce coronal mass ejections, clouds of plasma that travel through space, and can also impact Earth if they're directed toward us. The timing of this particular filament event meant it might contribute additional effects later in the week, layering on top of the ongoing high-speed stream. It's a reminder that the Sun is not a simple on-off system. It's complex, with multiple phenomena occurring simultaneously, each with their own timelines and potential Earth impacts, and the broader pattern for January is starting to become clear. This high-speed stream event is significant, but it's not isolated. Forecasters are already noting that mid-month looks active as well, with potential for additional geomagnetic storms as other coronal holes rotate into Earth-facing positions and as solar activity remains elevated. January is shaping up to be a month where space weather is a recurring theme, where auroras will be more common than usual, where those who pay attention to these things will find plenty to observe and study. And that's entirely consistent with being in solar maximum. This is what an active sun looks like, a series of events, overlapping and cascading, creating a dynamic space environment that keeps forecasters busy and aurora watchers hopeful. For anyone wondering what comes next, the answer is more of the same, at least for a while. The current stream will gradually weaken as Earth rotates out of the coronal hole's outflow. Solar wind speeds will decline, the magnetosphere will relax, and the auroral ovals will contract back toward the poles. But within days, the Sun will continue to rotate. And if new coronal holes form or if existing ones persist, there will be more opportunities for high-speed streams to impact Earth. And beyond coronal holes, there's always the possibility of solar flares and coronal mass ejections, which can produce even more dramatic space weather events if they're directed toward us. So the story isn't over. The overnight peak was a chapter, a significant moment in the ongoing narrative of how the Sun affects Earth, but the book is still being written, and we're living through its pages in real time. The fact that all of this played out while many people slept, while the world continued its routines, is a reminder of how much happens around us that we never directly perceive. The solar wind is invisible. The magnetosphere's compression can't be felt. The disturbances propagating through space go unnoticed unless you're watching the instruments or looking up at the sky in the right place at the right time, but they're happening constantly, and occasionally the effects become visible as auroras, as disruptions to technology, as stories that filter through the news and social media. And for those who do pay attention, who follow space weather and understand what's happening, these events are endlessly fascinating, a window into the dynamic relationship between Earth and Sun, a reminder that we're not isolated but embedded in a solar system where activity on the Sun ripples outward and affects everything in its path. Looking forward is as important as understanding what's already happened, because space weather isn't a single event, it's a continuous process. Right now, as you're hearing this, the solar wind stream is still impacting Earth, though past its peak intensity. And the question on everyone's mind who's been following this event is, what happens next? Do conditions simply return to normal, or is there more to come? The answer is layered, because while this particular high-speed stream will gradually weaken, the broader context of solar activity suggests that we're not done with geomagnetic disturbances for January, not by a long shot. First, let's talk about the immediate future, the next day or two. Forecasters expect the solar wind speed to remain elevated above normal, through at least January 10th. Earth is still positioned in the outflow from the coronal hole, though we're transitioning toward the trailing edge of the stream. That means the speed won't be as high as it was overnight, but it will still be significantly above baseline, and as long as the speed remains elevated and the magnetic field in the solar wind continues to interact with Earth's magnetosphere, geomagnetic activity will persist. The Kindex might not reach the levels it did overnight, but it will likely remain in the minor to moderate storm range, which means auroras will still be possible at northern latitudes. For aurora watchers, this is good news. Anyone who missed the overnight display has at least another opportunity, perhaps two, to head outside on a clear night and scan the northern horizon for signs of activity. The auroral oval may not extend as far south as it did during the peak, but it will still be present, still shimmering above the Arctic, and still visible to those positioned in the right locations with dark skies. And because the stream is expected to persist, there's a window of time, not just a fleeting moment, during which auroras are more likely than usual. It's a gift from the sun, in a sense, a prolonged period of enhanced activity that creates multiple opportunities to witness one of nature's most beautiful phenomena. But beyond the current stream, there's more happening on the sun that could affect Earth in the coming days. That filament eruption that occurred while the high-speed stream was impacting Earth, there's a possibility that it produced a coronal mass ejection directed toward us. CMEs are different from high-speed streams. While streams are continuous flows from coronal holes, CMEs are discrete clouds of plasma ejected from the sun during eruptions. They travel through space as expanding bubbles, and if one hits Earth, it can cause a sudden, intense geomagnetic storm. The timing of the filament eruption suggests that if a CME was produced, it might arrive later in the week, potentially around mid-January. Forecasters are monitoring the data, analysing coronagraph images from spacecraft that observe the sun's outer corona, trying to determine whether a CME is en route, and, if so, what its characteristics are. If a CME does arrive, it would layer on top of any residual effects from the high-speed stream, potentially creating stronger geomagnetic storm conditions than what we've experienced so far. CMEs can compress the magnetosphere even more dramatically than streams, and they often carry stronger magnetic fields, which can lead to more efficient coupling and more intense auroras. So the possibility of a CME impact mid-month is something that space weather forecasters are watching closely, and it's something that aurora watchers are hoping for, because CME-driven storms often produce the most spectacular displays. And beyond this particular week, the broader pattern for January is looking active. The sun's rotation is bringing other coronal holes into view, and some of them may also be positioned to send streams toward Earth as they rotate through Earth-facing longitude. The sun's rotation period is roughly 27 days, which means that if a coronal hole is large and persistent, it can impact Earth multiple times over the course of a few months as it rotates around. And with the sun in solar maximum, the formation of new coronal holes is common, meaning there's a steady supply of potential high-speed stream sources. Forecasters are already noting that the second half of January could see additional periods of elevated geomagnetic activity as these features rotate into position. This is the reality of living through solar maximum. Events like the one we're experiencing now aren't isolated anomalies. They're part of a pattern. The sun is active, its magnetic field is complex and chaotic, and the result is a steady drumbeat of space weather events that affect Earth with regularity. Some months are quieter than others, some storms are stronger than others, but the overall trend is clear. More activity, more auroras, more geomagnetic storms, more opportunities to witness and study the dynamic relationship between Earth and Sun. And this pattern will continue for at least another year or two, possibly longer, as the solar cycle progresses through its maximum phase and eventually begins to decline. What this means for the average person depends on their perspective. For aurora enthusiasts, it's an exciting time. More opportunities to see the northern lights, more chances for displays to extend to lower latitudes, more nights where heading outside with a camera might be rewarded with a spectacular show. For those who work with space-based technology, satellite operators, GPS system managers, power grid engineers, it's a time of increased vigilance. More geomagnetic storms mean more potential for disruptions, more need to monitor conditions and take protective measures when necessary. And for those simply curious about the universe, it's a reminder that we live in a dynamic solar system where the sun's behavior directly affects our planet, where the space around us is not empty, but filled with flowing plasma and magnetic fields, and where understanding those forces enriches our perspective on our place in the cosmos. The days ahead will reveal how this particular event concludes and what comes next. The current solar wind stream will weaken, Earth will rotate out of the coronal hole's direct line of fire, and conditions will begin to return toward normal. But normal during solar maximum is still more active than normal during solar minimum, and the potential for additional events is ever present. The Sun will continue to rotate, new coronal holes will form or existing ones will persist, and the chance for another high-speed stream impact is just a matter of time. And if that filament eruption did produce a CME, then mid-January could bring another round of geomagnetic storms, another surge of interest as people look up and wonder what's causing those strange lights in the sky. What's empowering about this moment is that we're not helpless or ignorant. We have the tools to monitor space weather, to predict when streams will arrive, to understand the causes and effects. We have a network of spacecraft observing the Sun, measuring the solar wind, tracking coronal holes and eruptions. We have models that simulate how the solar wind interacts with Earth's magnetosphere, forecasts that give us hours or days of warning before impacts occur. And we have a growing community of people who pay attention to these things, who share observations, who contribute to citizen science projects, who spread awareness about the beauty and science of space weather. This event, this high-speed stream from a coronal hole, is being watched, understood, and appreciated by thousands of people who might not have cared or known about such things a decade ago. That's progress, a sign that our relationship with the cosmos is becoming more informed, more engaged, more attuned to the reality that we're not separate from the universe, but an integral part of it. So as we look ahead, the message is clear. Stay curious, stay informed, and recognize that this is just one chapter in an ongoing story. The solar wind will keep blowing, the Sun will keep cycling through periods of high and low activity, and Earth will keep responding, its magnetosphere flexing and flowing, its auroras lighting up the polar skies, and we, living on this planet, get to witness it all, to study it, to be affected by it in ways both subtle and profound. The days ahead will bring new data, new events, new opportunities to learn and observe, and for those paying attention, it's a fascinating time to be alive, a moment in history when humanity's understanding of the Sun and its influence has never been deeper, and when the tools to explore that relationship are more accessible than ever before. Step back for a moment from the specifics of coronal holes and solar wind speeds, from kindices and auroras, and consider the broader picture. Earth is a planet bathed in radiation and particles from a star 93 million miles away. Every second of every day, the Sun is sending out light, heat, and a continuous stream of charged particles that flow through the solar system. And every second of every day, Earth's magnetic field is deflecting most of those particles, shaping the space around our planet, protecting the atmosphere and the life that thrives beneath it. This is the reality we live in, the cosmic environment that has existed for billions of years, long before humans evolved to wonder about it. The solar wind, for all its invisibility, is one of the fundamental forces that shape the space environment of every planet in the solar system. Mercury, closest to the Sun, is battered by intense solar wind and radiation, its lack of a significant atmosphere meaning the surface is directly exposed. Venus, despite its thick atmosphere, experiences solar wind interactions that strip away atmospheric particles over time. Mars, with its thin atmosphere and weak magnetic field, has lost much of its atmosphere to solar wind erosion over billions of years, and Earth, blessed with a strong magnetic field generated by a molten core, has retained its atmosphere, maintained its water, and allowed life to flourish, all because that magnetic field provides a shield against the relentless outflow from the Sun. But that shield isn't passive, it's dynamic, constantly responding to changes in the solar wind. When a high-speed stream arrives, the magnetosphere compresses. When the solar wind is calm, it expands. The boundary between Earth's magnetic field and the solar wind, called the magnetopause, moves inward and outward, flexing like a breathing organism. And the interactions at that boundary are complex, involving processes like magnetic reconnection, where field lines from the Sun and Earth snap and reconnect, allowing energy and particles to penetrate deeper into the magnetosphere. This is the invisible architecture that governs space weather, the underlying physics that determines whether a given solar wind stream produces a minor disturbance or a major geomagnetic storm. Humans have lived under the influence of solar wind and geomagnetic storms for our entire existence, though for most of that time we were unaware of the cause. Ancient civilizations saw auroras and interpreted them through the lens of their myths and beliefs: dragons in the sky, battles among gods, omens of change. They didn't know about charged particles or magnetic fields, but they knew that something extraordinary was happening, something that connected the heavens to their lives, and in a way they were right. The auroras were and are a connection, a visible manifestation of forces that link Earth to the Sun, a reminder that we're not isolated but part of a larger system. As humanity developed technology, our relationship with space weather changed. The first hints came in the 1800s when telegraph systems were disrupted during intense geomagnetic storms, currents induced in the wires causing operators to receive shocks and equipment to malfunction. The most famous of these events was the Carrington event of 1859, a massive solar storm that produced auroras visible as far south as the Caribbean and caused widespread disruptions to telegraph networks. It was humanity's first technological encounter with the power of space weather, and it served as a wake-up call that the sun's influence wasn't just about light and heat. It could directly affect systems we depended on. Today, our dependence on technology makes us more aware of space weather and more vulnerable to it. Satellites orbit in regions where the solar wind and geomagnetic storms are most intense. Power grids span continents, and induced currents during strong storms can cause transformers to overheat and fail. Communication systems rely on radio waves that travel through the ionosphere, and disturbances in that layer can degrade or block signals. GPS systems depend on precise timing and signal propagation, and geomagnetic storms can introduce errors. So while the solar wind has always been there, always been affecting Earth, our modern civilization has given us new reasons to care, new vulnerabilities that require monitoring and mitigation. But alongside the vulnerabilities, there's also wonder. The fact that we can now measure the solar wind in real time, that we can predict when high-speed streams will arrive, that we can watch the magnetosphere respond and see the auroras form, all of this is a triumph of science and engineering. We've placed spacecraft between Earth and the Sun, instruments that constantly stream data back to us, giving us a view of the solar wind that would have been unimaginable to previous generations. We've developed models that simulate the magnetosphere's behavior, allowing forecasters to predict geomagnetic storm intensity hours or even days in advance. And we've built a global network of ground-based instruments that measure magnetic field variations, auroral emissions, and ionospheric disturbances, creating a comprehensive picture of how space weather affects our planet. This ability to observe and understand is empowering. It means we're not at the mercy of forces we don't comprehend. We know what causes auroras, we know why geomagnetic storms occur, we know when high-speed streams are likely to arrive, and that knowledge allows us to prepare, to protect our technology, and to appreciate the beauty of the phenomena without fear. The solar wind isn't a threat in the sense that it will destroy life on Earth. Our magnetic field has been protecting us for billions of years and will continue to do so. But it is a force that we have to account for, to respect, and to study if we want to continue expanding our presence in space and relying on space-based technology. And there's a philosophical dimension to all of this that's worth acknowledging. The fact that invisible particles from the Sun are constantly hitting Earth, that our planet is embedded in a flow of solar plasma, that the space around us is not empty but filled with fields and forces, all of this challenges the intuitive sense that we're separate from the rest of the universe. We're not. We're intimately connected to the Sun, dependent on it not just for light and warmth, but shaped by its activity in ways both subtle and dramatic. The auroras are the most visible sign of that connection, but the connection runs deeper. Solar radiation drives our climate, solar particles shape the outer reaches of our atmosphere, and solar activity influences the space environment where our satellites operate. Living in this dynamic solar system, experiencing events like the current high-speed stream should inspire a sense of awe. The universe is not static. The Sun is not a simple light bulb. Space is not an empty void. There's activity, complexity, beauty, and power all around us, and we're fortunate to live in an era where we can observe and understand it. The charged particles slamming into Earth's magnetosphere right now left the Sun days ago, travelling across millions of miles of space, and their arrival creates light in our polar skies and disturbances in our magnetic field. That's extraordinary when you pause to think about it. It's a process that's been happening since Earth formed, and it will continue long after humanity is gone. But right now, in this moment, we're here to witness it, to measure it, to understand it, and to be moved by it. The invisible forces that shape our world are no longer quite so invisible. We've pulled back the curtain, developed the instruments and the theories to see what's really happening, and what we've found is that Earth is not a passive rock floating in space. It's an active participant in a complex dance with the Sun, a dance mediated by magnetic fields and flowing plasma, a dance that occasionally produces visible beauty in the form of auroras and invisible challenges in the form of geomagnetic storms. Understanding that dance, appreciating its intricacy, and recognizing our place within it, that's the deeper lesson of events like the one unfolding right now. So here we are, at the end of a journey through space weather, through solar wind and coronal holes, through magnetospheres and auroras, and as this video comes to a close, the event we've been discussing is still ongoing. The solar wind is still hitting Earth at elevated speeds, though the peak has passed. The magnetosphere is still responding, still compressed, still funneling energy toward the poles, and the auroras are still lighting up northern skies for those fortunate enough to be in the right place at the right time. This isn't a story that is neatly concluded. It's a story still being written, still unfolding, and you're living through it right now. What I hope you take away from this is not just an understanding of what's happening, but an appreciation for why it matters. The Sun is not a distant, irrelevant object. It's the central force in our solar system, the source of energy that drives our weather, our climate, and yes, our space weather. And right now, the Sun is in an active phase, a period where its magnetic field is chaotic, where coronal holes open and send high-speed streams toward Earth, where eruptions occur and geomagnetic storms result. This is solar maximum, and it's a time when those of us paying attention get to see the Sun's influence on Earth in ways that are both measurable and visible. If you're in a northern state, if you have clear skies tonight or tomorrow night, go outside, look north. You might just see a faint glow on the horizon, or if conditions are favourable, you might see shimmering curtains of green light dancing overhead. That's the solar wind. That's the charged particles from the coronal hole on the Sun. That's the magnetosphere funneling energy into the atmosphere and creating light. And knowing what causes it, understanding the chain of events from the Sun's magnetic field to Earth's auroral zones, makes the experience richer, more meaningful. You're not just seeing pretty lights, you're witnessing the direct interaction between Earth and Sun, a process that's ancient and ongoing and beautiful. And if you're not in a position to see auroras, if you're at a latitude where they're not visible even during storms, don't think this event doesn't affect you. You're still part of this story. The solar wind is still impacting Earth, the magnetosphere is still responding, and the invisible forces we've discussed are still at play above your head. The fact that we live in an age where we can measure these forces, predict them, understand them, and share that knowledge with anyone who's curious, that's something to celebrate. A century ago, most of this would have been unknown. 2 centuries ago, the very idea of solar wind would have seemed absurd. But now, we know. We've figured it out, piece by piece, and we continue to learn more with every event, every observation, every data point. I want to encourage you to stay engaged with this topic. Space weather isn't going away. As long as the Sun is in solar maximum, events like this will occur with regularity. More coronal holes will form, more high-speed streams will impact Earth, more geomagnetic storms will light up auroras and challenge our technology. And if you're subscribed to this channel, you'll be among the first to know when the next event is happening, what's causing it, and what it means. So if you haven't already, hit that subscribe button. Join the community of people who find this stuff fascinating, who want to understand the universe we live in, who appreciate the blend of beauty and science that space weather represents. And drop a comment. Tell me where you're watching from. Tell me if you've seen auroras during this event or if you're hoping to catch them tonight. Share your thoughts, your questions, your experiences, because this is a community effort, a shared journey of discovery and wonder. We're all living on the same planet, all under the same sun, all affected by the same solar wind. And when we come together to learn and discuss and appreciate, it enriches the experience for everyone. Looking ahead, the story continues. The current solar wind stream will weaken over the next day or two, as Earth rotates out of the coronal hole's path, but mid-January is still looking active, with the potential for additional geomagnetic storms if that filament eruption produced a coronal mass ejection, or if other coronal holes rotate into position. And beyond January, the Sun remains in solar maximum, which means months of elevated activity, months of opportunities to observe space weather in action, months where the dynamic nature of our star will be on full display. This is not a time for fear, it's a time for awareness, for curiosity, for engagement. The solar wind is part of the environment we live in, and understanding it makes us more informed, more prepared, and more connected to the cosmos. The high-speed stream hitting Earth right now is a reminder that we're not isolated, that the Sun's activity directly affects our planet, and that the invisible forces shaping our space environment are worth paying attention to. And the auroras, those beautiful ribbons of light, are nature's way of making those forces visible, of giving us a glimpse into processes that would otherwise remain hidden. So as you go about your day, as you continue with your routines, remember that above your head, the solar wind is flowing, the magnetosphere is responding, and the dance between Earth and Sun continues. It's been happening for billions of years, and it will continue for billions more. But right now, in this moment, you have the knowledge to understand it, the tools to observe it, and the opportunity to appreciate it. And that's a gift, a product of centuries of scientific inquiry, of countless researchers dedicating their lives to unraveling the mysteries of the Sun and its influence on our world. Thank you for watching, for spending these minutes with me as we explored what's happening right now, why a giant hole opened on the Sun, and what it means for Earth. Thank you for your curiosity, your attention, and your willingness to dive deep into a topic that's complex but endlessly rewarding. The universe is vast and strange and beautiful, and events like this high-speed solar wind stream are a window into that beauty. Keep looking up, keep asking questions, and keep seeking to understand the forces that shape our world, and I'll be here, covering the next event, the next storm, the next chapter, in the ongoing story of Earth's relationship with the Sun. Until next time, stay curious, stay informed, and remember, we're all watching the Sun together.